This is a very interesting news story. So, breathtaking new map of the X-ray universe, and this is the 19th of June 2020. Today's the 21st of June, and the time of this recording is 10:51 p.m. So, just reading through it. So, behold the hot, energetic universe. A German-Russian space telescope has just acquired a breakthrough map of the sky that traces the heavens in X-rays. The image records a lot of the violent action in the cosmos, instances where matter is being accelerated, heated, and shredded. Feasting black holes, exploding stars, and searing hot gas. The data comes from the eRosetta instrument mounted on Spectre RG. This orbiting telescope was launched in July last year and dispatched to an observing position some 1.5 million kilometers from Earth. Once commissioned and declared fully operational in December, it was left to slowly rotate and scan the depths of space. eRosetta's first all-sky dataset, represented in the image at the top of this page, was completed only last week. It records over 1 million sources of X-rays. That's actually pretty much the same number as had been detected in the whole history of X-ray astronomy going back 60 years. We have basically doubled the known sources in just 6 months, said Kirpal Nandra, who heads the High Energy Astrophysics Group at the Max Planck Institute of Extraterrestrial Physics MPE in Garching, Germany. The data is truly stunning, and I think what we are doing here will revolutionize X-ray astronomy, he told BBC News. So have a look at the Vela supernova remnant. The Vela supernova remnant is a mere 800 light-years from Earth. The map uses the so-called ATOF projection, which unwraps the sphere of the sky onto an ellipse. The band across the middle is the plane of our Milky Way galaxy, with the center of the galaxy in the middle of the ellipse. The image has been encoded with color to help describe what's going on. Blues represent higher energy X-rays, 1 to 2.5 kilo electron volts (keV). Greens are mid-range, 0.6 to 1 kilo electron volts, and reds are lower energy, 0.3 to 0.6 kilo electron volts. Much of the galaxy's plane is dominated by highly energetic sources. In part, that's because copious amounts of gas and dust have absorbed and filtered out the lower energy radiation. Sources include stars with strong magnetically active and extremely hot atmospheres. The greens and yellows that draw a kind of mushroom feature covering a great swathe of the map represent hot gas inside and just outside our galaxy. This material imprints information about the formation and evolution of the Milky Way. Some of the biggest blotches are well-known actors on the sky. The bright yellow patch just above the plane on the far right is a concentration of supernova remnants, the wreckage of stars that have exploded and whose shockwaves have superheated surrounding cocoon of dust and gas. This particular patch is dominated by the Vela supernova remnant. This was an explosion that happened thousands of years ago, but a mere 800 light-years from Earth. Look next at the diffuse red glow at the top and bottom of the map. This is largely X-ray emission from hot gas well beyond our galaxy. And in the white speckles, we are seeing principally the signature of supermassive black holes. Indeed, about 80% of all the sources contained in the new map are the gargantuan black holes that reside at the centers of distant galaxies. They pump out X-rays as their immense gravitational pull draws in and eviscerates matter. Some of the supermassive black holes making an appearance in the map are seen when the universe was younger than 1 billion years old, less than 10% of its present age. Now, Spectre RG and its eRosetta instrument intend to gather 7 more all-sky surveys over the next 3.5 years. This will enable the telescope to refine its data, to remove artifacts and noise, but also to sense deeper into the cosmos and pick up the faint sources that would otherwise be beyond detection. One key goal is to map the distribution of the hot X-emitting gas that illuminates the great cluster of galaxies. Astronomers hope that this information can lead them to some fresh insights on how the universe is structured and how it has changed over time. It's possible there may be some clues in this project about the nature of dark energy, the mysterious force that appears to be pushing the cosmos apart at an ever-accelerating rate. That's the big prize, but it would only come at the end of the mission, explained Professor Nandra. 8 surveys allows us to go really deep into the distant universe. Basically, we're trying to detect all the clusters of galaxies in the universe above a certain mass limit. We've got a nice sample already, maybe around 10,000, but we're hoping to get at least 100,000 clusters of galaxies. E Rosetta is the German element on Spectre RG. It takes up most of the room on the spacecraft bus or chassis, but it sits next to a Russian instrument known as ART-XC, which is sensitive to high energies, up to 30 kilo electron volts. Both E Rosetta and ART-XC use a cluster of 7 tubular mirror modules to coral X-ray light down onto their sensitive camera detectors. So the question is, convert the measurements into standard form. Also convert the electron volts into joules. So number one, this is in the BBC article, but it sits next to a Russian instrument known as ART-XC, which is sensitive to high energies up to 30 kilo electron volts. So convert the 30 kilo electron volts into joules. Number two, the image has been encoded with color to help describe what's going on. Blues represent higher energy X-rays, 1 to 2.3 kilo electron volts keV. Greens are mid-range, 0.6 to 1 kilo electron volts, and reds are lower energy, 0.3 to 0.6 kilo electron volts. Number three, this orbiting telescope was launched in July last year and dispatched to an observing position some 1.5 million kilometers from Earth. Once commissioned and declared fully operational in December, it was left to slowly rotate and scan the depths of space. So the task is, what is 1.5 million kilometers in standard form, and and how many light years is 1.5 million kilometers? Number four, the Venus supernova remnant is a mere 800 light years from Earth. What is the distance in meters? 1 light year is the time it takes for a light particle wave to travel in 1 year. Speed of light is 3 times 10 to the power of 8 meters per second. The task is to convert the electron volts into joules. So the first one is convert the 30 kilo electron volts into joules. And then you've got the blue, green, red, and you've got to convert the 1.5 million kilometers into standard form. Just as exercise, what is how many light years is 1.5 million kilometers? And 800 light years, what is how many meters is that? Okay, so let's start with 30 kilo electron volts. Now we start with the equation. The voltage is energy per charge. So here we have voltage is energy divided by charge, and this is 1 volt. So 1 volt would be 1 joule per coulomb. So what is 1 electron volt? Alright, so if you have, let's just say you've got 2 plates and the difference between them is 1 volt, and you've got a charge of 1 electron, and the charge of 1 electron is 1.6 times 10 to the minus 19 coulombs. So so 1 volt is equal to question mark divided by 1.6 times 10 to the minus 19 coulombs. What's the joules? Well, you times that to that side, so that's, you times that. So then you have 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So that is the conversion. So 30 kilo electron volts would be 30 times 10 cubed electron volts. So that's 3 times 10 to the 4. And to convert that into joules, you just times this by 3 times 10 to the 4. So that's the same as 3 times 10, that's 4.8, and that is So the question is to convert the blue range into joules. Now I'm just going to convert the 1 kilo electron volts into joules, and then I'm going to times that value as the conversion. So so 1 kilo electron volt is 1 times 10 to the power 3 electron volts. And we know that 1 electron volt is 1.6 times 10 to the minus 19 joules. So 1 kilo electron volt is just that times this. So then you have 1.6 times 10 to the minus 16 joules. So therefore the range for the blue one is 1.6 times 10 to the minus 16 joules to, so, and then there's just this number times 2.3. And on a calculator, 1.6 times 2.3, I get 3.7 to 1 decimal place. What about the green region? So the green region is 0.6 to 1. So you know from 1 was 1.6. And then it's just 0.6 times that. And that is, well, 6 times is 96. So this would be 0.96 times 10 to the minus 16, or it is equal to 9.6 times 10 to the minus 17. And what about the red? The red was 0.3 to 0.6. So let's see. Okay, so it's just this times this, isn't it? So 0.3 times 1.6 times 10 to the minus 19. Sorry, minus 16. What is 1 light year? Now, the light year is not the time, it is a distance. So it is the distance of light traveling in 1 year. Right, so we need to work out, the distance. So we know the speed of light is 3 times 10 to the power 8 meters per second. So that's the speed. And time. So let's just say 365.25 times 24 hours in a day, 60 minutes in an hour, and 60 seconds in 1 minute. So if you do 3 times 10 to the power 8 times 365.25 times 24 hours times 60 minutes and 60 seconds, you get 9.47 times 10 to the power 15. meters to 2 decimal places. Alright, so the question is, how many light years is 1.5 million kilometers? So that is 1.6 times 10 to the power of 6 kilometers. You still need to convert that into meters, so that's 1.5 times 10 to the 9. And so you need to find the fraction of that. So it is 1.5 times 10 to the 9, 9.47 times 10 to the power 15. So alright, so it's 1.5 times 10 to the power 9 divided by 9.47 times 10 to the power 15. You get 1.58 times 10 to the minus 7. So it's 1.58 times 10 to the minus 7 light years. That is a very small number. You could convert that into, because that is a distance. What about months? Would you convert that into month? 1.58 times 10 to the minus 7 light years into months. Okay, let's just leave that for the moment. And then you have 800 light years. So 800 light years is how many meters? Well, you know that 1 light year is this. So 800 light years, Ly meaning light years, times that by 800. So 800 light years is equal to 7.6 to 1 decimal place times 10 to the 18, or 7.58 times 10 to the 18 meters to 2 decimal places.